Okay, the first thing I want to talk to you about is whenever we combine metals together. So in this case, we're going to look at copper, zinc, and tin. If we take the element zinc, you can find it on the periodic table, and combine a little bit of it with a lot of copper, mix them together, you get something called brass. It looks different than its components, zinc and copper. Now you might want to say, oh, Mr. Kasinger, that's a chemical reaction that you're doing whenever you combine this zinc and copper to make brass. No, 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 no. If you you can look at this picture here of a brass cube. You have copper metal and some liquefied zinc metal. You can separate the brass simply by heating it up, and the zinc and copper will have different densities, and so you can just separate them doing a physical change. So the combination of zinc and copper is not a chemical reaction, you're just mixing them together. Another thing that you can mix copper with is the metal tin. These two come together and you're going to have bronze. And I have an example. It's not always tin, the other metal, but whenever copper is mixed with metals like tin, you get bronze. Tin is an element, copper is an element. Mix the two together, you have something called bronze, but it again is just a mixture, meaning the little atoms of copper, I'll draw some copper out here, are just mixed in with the tin atoms, or you can look at brass and say the copper's mixed in with the zinc atoms. And that's what's happening. Whenever this does happen, though, you can pick any part of this. Here my examples are the for bronze is the Olympic bronze medal. That's what bronze looks like. It looks very similar to copper. And here's some old bronze that's it's changed color a little bit because it's reacted with the air, but this is some old armor made out of bronze. So bronze and brass get confused a lot. They are different, and they do look different if you compare them side by side. So these are not chemical reactions that are occurring, and these are not pure substances. They are made out of two different elements, and so two different atoms. So we're going to call these metal alloys, which are solutions, which are homogeneous mixtures. These are all homogeneous mixtures, just mixtures of metal atoms together. So it's a special type of homogeneous mixture, somewhat, but it still has the same definition as all the others. But you might hear them referred to as metal alloys, a mixture of two different metals. All right, so let's keep our review going. All right, homogeneous or heterogeneous element or compound. All right, let's take a look at some examples here. We have some soda here, or soda pop or Coke or whatever you want to call it. We have some sort of fizzy drink here. If you just looked at this portion of the drink, you'd say, oh yeah, it looks the same throughout pretty much. So that's a homogeneous mixture, or it's an element or a compound. Well, you know it's not an element, and you know it's not a compound, because if you look on the back of a Coke, it's made of a whole bunch of different elements and compounds. So it's not a pure substance, so it's not element or compound. So it's either going to be homogeneous or heterogeneous. Well, if you just looked at this portion right here and didn't look at the suds, the bubbly part, the carbonated gas, the carbon dioxide gas, yeah, you could say, oh, it's all the same throughout. But soda's not just that. It's not just a liquid. It has a gas in it. It has the carbon dioxide, the carbonation, that fizziness to it. And it has, so you can see that fizziness in the form of the foam on top, or if you look close at this picture, you can see the little bubbles there that are collecting beside the ice. So if I ask you if soda pop is a homogeneous or heterogeneous mixture, you would say heterogeneous. Hetero. Okay, let's look at another one. Air. It's what we breathe. But is it just oxygen? No, it's not just oxygen. It's actually mainly nitrogen. A lot of N2. Um, nitrogen is in our air. Oxygen is in our air, O2. And what's the thing we breathe out? Oh yeah, carbon dioxide. That's all in our air. So air has a compound in it. It has two different elements in it. They're all mixed together. You can't pick out one part of the air and it have a different consistency than another part, really. So it is homogeneous. Alright, let's keep moving on. An egg. Let's look at this egg here. Well, if we just look at this egg, it looks all the same, right? Or we just look at this one, or these two look a little different because the coloring is different. But if we look inside of an egg, you'd see that there's actually like yolk in here, the yolk, and then the white part surrounds it, right, on the inside of this. So this has different parts to it, so that would be a heterogeneous mixture, right? Alright, let's move on to Kool-Aid. Let's move on to this guy right here. Kool-Aid. We're not looking at the ice in it. We dropped some ice in it. We know that if it was Kool-Aid and the ice, it's of course hetero, but we're not looking at the ice. We're just looking at Kool-Aid. Well, if you mix your Kool-Aid up well enough, it dissolves all the sugar. It dissolves the Kool-Aid mixture, the mix. So it's all dissolved. It's evenly dispersed throughout, and so that would be homo. Now, if you add carbonation to your Kool-Aid, then it becomes hetero because the bubbles don't completely mix with the liquid. Okay, the next one, steel. It has a little bit, and you might not know this, but steel has a little bit of carbon mixed in with iron. You can see some of the iron rusting in this picture. So these two combine, it's like the page before. We combine two elements, we just mix them. That's what they do with this. Our steel, they just mix the carbon and iron. So this is and it looks the same throughout. I know there's rusting on this, but if you just look at a fresh piece of steel, it looks the same throughout. This is homogeneous mixture. It's not a compound. They don't combine the iron and carbon to make iron carbon or anything like that. It's just carbon atoms, like here, mixed with iron atoms. They're just mixed together. And they're evenly mixed, so it's homogeneous. Let's look at another one. Milk. This one's a little bit more difficult. If we look at milk, and from the lab, you know that it's a mixture. Now, whenever you go to college, they're going to tell you that it's hetero. But for me, if you say it's homo, I'm fine with that. The milk that you look at in your refrigerator, it looks the same throughout. You taste the beginning, it more than likely tastes the same at the end. So if you just drink this portion here, set it in your fridge, tomorrow you drink a little bit more, and then the next day you drink a little bit more. These all will taste basically the same to you. So if you call it a homo, that's fine. A homogeneous mixture, that's fine. If you call it hetero, that's fine. Just know that's a mixture. Alright, we're running out of time, so I'm going to have to make a part 2.